Hello, welcome to EPG Pathshala Biophysics, Paper 2 Quantum Biophysics. I am Angshuman Lahiri, Associate Professor, Department of Biophysics, Molecular Biology and Bioinformatics, University of Calcutta. In this paper today, we are going to take up Module 11, that is hybrid orbitals in carbon compounds. In one of the previous modules, that is Module 9, we took up the Born-Oppenheimer approximation and the valence bond theory for hydrogen molecule. Although valence bond theory was successful in giving a theoretical explanation to the intuitive shared electron pair model of chemical bonding, the simple application of the theory encountered many conceptual problems later. One interesting example is carbon, whose bonding characteristics have crucial significance for the structure and conformation of all biological macromolecules. According to valence bond theory, carbon should have formed the compound CH2 since it has only two unpaired electrons in its valence shell. However, as we all know, CH2 is a very unstable molecule, whereas the molecule methane, CH4, is much more stable, although it is not likely to occur according to the valence bond theory. Also, the bonding geometry of methane is tetrahedral, quite different from the mutually perpendicular geometry of the p orbitals. This, however, becomes easy to understand if we realize that orbitals during bond formation should in general be different from atomic orbitals in individual atoms. The shape and geometry of the atomic orbitals were determined under the condition of a central nuclear charge, whereas for a molecule the problem is necessarily a multicenter one, and thus the orbitals will be in general different functions. The method of molecular orbitals discussed in the previous module provides us with a sophisticated theoretical technique to address this issue. However, there is also another less complicated approach known as the hybrid orbital theory, which was introduced by Linus Pauling from 1931 in several seminal and revolutionary publications. In this module, we will discuss the hybrid orbital method and give examples of its application for simple cases involving carbon compounds mostly. In this module, our objectives are to acquire a basic understanding of the necessity of introducing hybrid orbitals, to have an idea about the relation between valence bond theory, hybrid orbital theory, and molecular orbital theory, to learn how to apply it for the simple situation of sp hybridization, to gain understanding of how it may be applied for the more complicated cases of sp2 and sp3 hybridization. We now discuss the case of beryllium hydride and sp hybridization. Let us begin with our discussion with the examination of the case of beryllium hydride. Beryllium is divalent in this molecule. However, if we consider that the ground state electron configuration as 1s2, 2s2 for beryllium, the two electrons in the 2s orbital have opposite spins, so that according to the valence bond theory, these electrons should not show preference for interacting with other atoms. Experimentally, it is also known that the two beryllium hydrogen bonds are equivalent and the molecule is linear. That excludes the situation when one of the electrons is in the s orbital and the other occupies a p orbital. We therefore need to construct wave functions that will correspond to electron density spread out in two directions 180 degrees apart. Mathematically, this can be done in very many ways, but the hybrid orbital method prefers to construct these functions, which we call hybrid orbitals, by combining the atomic s, p, d and f functions. To enforce the opposite directionality of the two beryllium-hydrogen bonds, a linear combination of the beryllium 2s orbital and one of the beryllium 2p orbital, for example 2pz, is taken. So one of the hybrid orbital, say xi, will be a linear combination of the beryllium 2s orbital and beryllium 2pz orbitals, and suppose the coefficients are A1 and B1 respectively. Another hybrid orbital, xi prime, will be a linear combination of the same 2s and 2pz orbitals of beryllium, but suppose the coefficients are A2 and B2. Then the two bonds can be written as phi equals C1 1 SA plus C2 xi and phi prime equals C1 prime 1 SA plus C2 prime xi prime, where two hydrogen atoms have contributed the 1 SA and 1 SB orbitals. Our task now is to determine the forms of xi and xi prime such that phi and phi prime form oppositely directed but otherwise identical bond orbitals. Since one 2s orbital is distributed among two hybrid orbitals, we will have A1 square plus A2 square equals 1, and from the symmetry of the problem, we must have A1 equals A2. Therefore, it's very simple to find that A1 must be equal to A2, which must be equal to 1 by root 2. On the other hand, if we normalize xi, that will give us the condition A1 square plus B1 square equals 1. If we now take into account all these conditions, then the substitution of the value of A1 leads to B1 equals 1 by root 2. If we now impose the condition that xi and xi prime should be orthogonal to each other, we get an additional relation, that is A1 A2 plus B1 B2 equal to 0. If we now substitute the previously determined quantities, then that will give us B2 equals minus 1 by root 2. So finally, the hybrid orbitals will be xi equals 1 by root 2, 2s plus 2pz, xi prime equals 1 by root 2, 2s minus 2pz. Since these orbitals are made up of one s orbital and one p orbital, they are called sp hybrid orbitals. The formation of beryllium hydride molecule is through overlap of the hydrogen 1s orbitals with each of the sp hybrid orbitals. Therefore, the electronic configuration of beryllium hydride molecule will be described as K phi 2 phi prime 2. Next, we take up the case of sp2 hybrid orbitals. As you can see in the figure, the molecule ethylene, which has a formula C2H4, has a planar geometry and it provides us with another example of molecular structure where the idea of hybridization can be successfully employed. The electronic configuration of carbon is 1s2, 2s2, 2p2. In ethylene, one finds that experimental observations are best explained by assuming that one 2s orbital in each carbon is hybridizing with 2p orbitals. Remaining one of the 2p orbitals of carbon, say 2pz, remains unhybridized and contributes a p electron to the molecule. Therefore, 2p electrons will be directed along the z-axis, which will form the pi bond. The 2s, 2px and 2py functions mix up to form a system of three identical sp2 hybrid orbitals in the xy plane, which we will call Ψ1, Ψ2 and Ψ3. It can be shown that they are obtained by the linear combinations Ψ1 equals square root of 1 by 3, Ψ2s square root of 2 by 3, Ψ2px, Ψ2 equals square root of 1 by 3, Ψ2s minus square root of 1 by 6, Ψ2px plus square root of 1 by 2, Ψ2py. Ψ3 equals square root of 1 by 3, Ψ2s minus square root of 1 by 6, Ψ2px minus square root of 1 by 2, Ψ2py. The orbitals 2s, 2px and 2py have relative values on the xy plane, which corresponds to theta equals 90 degree, Ψ2s is to Ψ2px is to Ψ2py, that is equal to 1 is to root 3 cos phi is to root 3 sin phi. It is easy to observe that Ψ2s equals 1 and Ψ2px equals root 3 along the x-axis, which is obtained by putting phi equals 0 in the last equation. We obtain capital Ψ1 equals 1.99, which is its maximum extension along x-axis. The orbitals Ψ2 and Ψ3 will also have similar shape as Ψ1, although they extend towards different directions on the xy plane. The three hybrid orbitals demonstrate what we called a trigonal symmetry. The angle between any two of these hybrid orbitals is 120 degree, leading to a planar structure for ethylene. To see this, we again start from the last equation. Putting the relative values for the orbitals into the second of the equations in 9 for Ψ2 and requiring that d Ψ2 d phi equals 0 for the maximum extension of the orbital, we obtain tan phi equals minus square root of 3. It follows that phi equals 120 degree. So the hybrid orbital will experience its maximum at an angle of 120 degree to the x-axis. In a similar manner, It can be shown by using the last equation in 9 that the hybrid orbital Ψ3 will have its maximum at an angle 240 degree to the x-axis on the xy plane. Therefore, if we consider all three hybrid orbitals Ψ1, Ψ2 and Ψ3 of a carbon atom in the case of sp2 hybridization, they will be at an angle of 120 degree to one another on the xy plane. For the molecule ethylene, this forms the sigma bond structure. The same consideration applies for other planar molecules like benzene. Let us now investigate why the coefficients in the three equations in 9 have such values. We start from the general expansion. Ψ1 equals A1 Ψ2s plus B1 Ψ2px plus C1 Ψ2py. Ψ2 equals A2 Ψ2s plus B2 Ψ2px plus C2 Ψ2py. Ψ3 equals A3 Ψ2s plus B3 Ψ2px plus C3 Ψ2py. Since the hybrid orbitals have directional properties, we assume that Ψ1 is directed along the x-axis so that any two carbons brought together along the x-axis will have maximum overlap. That means that we can put the coefficient C1 equals 0. Since the 2s orbital has spherical symmetry and the three new wave functions are equivalent, it will be equally distributed so that A1 square equals A2 square equals A3 square, and that will be equal to 1/3. This leaves us with A1 equals A2 equals A3 equals square root of 1/3. We now proceed step by step to get the other coefficients. Since Ψ1 is normalized to unity and C1 equals 0, we must have A1 square plus B1 square equals 1. Substituting the value of A1, we obtain B1 equals square root of 2/3. Requiring further that Ψ1 is orthogonal to Ψ2, we have the condition A1A2 plus B1B2 equals 0 after taking into account that C1 equals 0. Substituting the values of the coefficients A1, A2 and B1, we obtain B2 equals minus square root of 1/6. Now since Ψ2 is normalized to unity, we have A2 square plus B2 square plus C2 square equals 1. Substituting the values of the coefficients A2 and B2, we now obtain C2 equals square root of half. Since Ψ1 is orthogonal to Ψ3 and C1 equals 0, we have A1A3 plus B1B3 equals 0. Putting the values of the coefficients A1, A3 and B1, we obtain B3 equals minus square root of 1/6. Also, since Ψ2 is orthogonal to Ψ3, we will have A2A3 plus B2B3 plus C2C3 equals 0. Putting the values of all the other coefficients, we find C3 equals minus square root of half. As we have already seen, the three planar hybrid orbitals are oriented at 120 degree to one another at each carbon atom. These constitute the sigma orbitals, while the pi orbitals, 2pz orbitals of carbon are perpendicular to this plane. The pi orbitals of the two carbon atoms in ethylene overlap laterally to make a pi bond apart from the sigma bond formed from the sp2 hybridized orbitals. We now discuss the case of sp3 hybrid orbitals, and we take the example of methane. Methane, which has a formula CH4, has a tetrahedral structure, as you can see in the figure, with the carbon atom at the vertex and 4 perfectly symmetrical and identical CH bonds. The angle between the bonds is also the same and is about 109 degrees. If we consider that one of the valence electrons of carbon is a 2s electron with spherical charge distribution, and the other 3 are 2p electrons with extended charge distributions, this is something which is very difficult to explain, since the nature of overlap is expected to be different for different type of orbitals. So as before, we assume that the atomic orbitals of carbon in CH4 do not remain as pure s and p orbitals. Rather, they will form hybrids or mixtures of one s orbital and the 3 p orbitals, and the way they must be mixed is such that the resulting sp3 hybrid orbitals of carbon are all equivalent. There are 4 such hybrid orbitals. In CH4, these hybrid orbitals yield perfectly symmetrical charge distribution that fits the tetrahedral symmetry. Mathematically, one proceeds by constructing linearly independent combinations of the 4 pure atomic orbitals Ψ2s, Ψ2px, Ψ2py, Ψ2pz of carbon. These combinations can be written as Ψ1 equals A1 Ψ2s plus B1 Ψ2px plus C1 Ψ2py plus D1 Ψ2pz. Ψ2 equals A2 Ψ2s plus B2 Ψ2px plus C2 Ψ2py plus D2 Ψ2pz. Similarly, for the other orbitals, the 16 coefficients that occur in those linear combinations have to be determined so that the principle of maximum overlapping is satisfied, leading to the formation of the most stable state of the molecule. The result of this requirement is the tetrahedral symmetry of the molecule. Also, the 4 hybrid orbitals Ψi, where I goes from 1 to 4, of carbon should be orthonormal to one another. Recall that the pure orbitals Ψi, where I, where 2s, 2px, 2py and 2pz already constitute an orthonormal set. From solutions of the angular parts of wave functions of the hydrogen atom, it is known that the relative values of these atomic orbitals are Ψ2s is to Ψ2px is to Ψ2py is to Ψ2pz equals 1 is to root 3 sin theta cos phi is to root 3 sin theta sin phi is to root 3 cos theta. Let us now discuss briefly how one proceeds to determine those 16 coefficients. We select the x-axis to lie along the direction of the hybrid atomic orbital Ψ1, which is usually referred to as the first bond wave function. The 2py and the 2pz atomic orbitals are 0 along this direction. Therefore, the coefficients C1 equals D1 equals 0. And so the first equation becomes psi1 equals A1 psi2s plus B1 psi2px. Since psi1 should be normalized to unity, while psi2s and psi2px are orthonormal wave functions, we find that A1 square plus B1 square equals to 1, so that psi1 equals A1 psi2s plus square root of 1 minus A1 square psi2px. For the first hybrid orbital psi1 directed along the x-axis, theta equals pi by 2 and phi equals 0. Therefore, we put psi2s equals 1 and psi2px equals square root of 3, and substituting in equation 15, we get psi1 equals A1 plus square root of 3 into 1 minus A1 square. To determine A1, we invoke the condition of energy minimum or the maximum bond strength. This requires maximum overlap of the bond functions and hence maximum extension of psi1 along the x-axis. This is obtained by the condition d psi1 d A1 equals 0, which gives A1 equals half and B1 equals square root of 3 by 2. Therefore, we get psi1 equals half psi2s plus square root of 3 by 2 psi2px. If we take psi2s equals 1 and psi2px equals square root of 3 along the x-axis as before, the value of the hybrid orbital psi1 equals 2.0, which is its maximum value along the x direction. This is clearly greater than root 3, the maximum value of the 2px orbital alone. Thus, the formation of the hybrid orbital psi1 is expected to result in greater overlap compared to pure 2px orbital, thus favoring the hybridization. Continuing in the same line as the previous section, one can show that the orbitals for the case of sp3 hybridization can be constructed as psi1 equals half psi2s plus square root of 3 by 2 psi2px, psi2 equals half psi2s minus 1 by 2 root 3 psi2px plus square root of 2 by 3 psi2px, psi3 equals half psi2s minus 1 by 2 root 3 psi2px plus 1 by root 2 psi2py minus 1 by root 6 psi2pz, psi4 equals half psi2s minus 1 by 2 root 3 psi2px minus 1 by root 2 psi2py minus 1 by root 6 psi2pz. Calculation of the angle between any two bonds in the tetrahedral molecule methane CH4 according to the above scheme also finds its value to be 109 degree 28 minute in excellent agreement with experimental observations. So let us briefly summarize the main points of this module. The hybrid orbital method was developed to address situations where valence bond method could not predict the correct valence or bonding geometry. The hybrid orbital method combines specific atomic orbitals, hybridization, into equal number of hybrid orbitals reproducing the experimentally observed bonding geometry. Taking into consideration the geometry of the molecules involved, it is straightforward to construct the hybrid orbitals as linear combinations of specific atomic orbitals. And the coefficients of these linear combinations can be evaluated using the orthonormality of the orbitals and the principle of maximization of the hybrid orbitals for maximum overlap. Thank you.